All right, this is going to be part 2 of your work, power, energy, and machines review. I did 1 through 12 on the previous one. I'll do 13 through 19 on this one. So I have number 13 that I'm going to start with. Number 13 tells us that we have a projectile. So we have a mass 1 of, and we're going to say this is our projectile, of 1 kilogram. And we're told it's going a velocity of 10 meters per second. And then we also have a launcher. That's a bad spelling. Sorry about that. All right. That has a mass of 10 kilograms. And because it has the same momenta, which means that it has the same velocities roughly, because momenta is mass times velocity, if they're equal and opposite, then that would actually mean that um, its velocity would have to be 1 meter per second. So if that's the case, because the momentum of this one is P equals mv, so that would be 1 times 10. So this one would have 10 as its momentum as well, P equals mv. So if we know it's 10 equals 10 v, we could find out that this v is 1. It's divided by 10 divided by 10. Okay? Well, if we know that information, then we could find the kinetic energies, because we're supposed to prove that the projectile is, or the launcher is 10 times as much potential energy. So Ke is mv squared over 2. So we have 1 kilogram times 10 meters per second squared divided by 2. That means my projectile has a kinetic energy of 50 joules. And if I do the same thing over here for my launcher, I'll go ahead and make it in yellow. I have 10 kilograms times 1 squared divided by 2, which gives me 5 joules. So 50 divided by 5 gives me 10 times as much. So that proves that it's 10 times more. The launcher has 10 times more kinetic energy than the projectile does. Moving on. Number 14. We have a hydraulic machine that is shown on your worksheet, and you observe that when a small piston is pushed down a distance of 10 centimeters, so that would be my input distance, my DI is going to be 10 centimeters, which converted is 0.1 meters. A large piston, which is going to be my DO, is moved out. It raises, so it raises 1 centimeter, which converted is 0.01 meter. If the small piston is pushed down with a force, so that's my input force, or my Fi, of 200 newtons, then I want to know how much output force there's going to be. Well, remember, work in should equal work out. So FIDI should equal FODO. So FD equals photo. All right. So we have 200 newtons times 0.1 meters equals FO times 0.01 meters. So we divide by 0.01 meters on each side. Whatever you do to one side, you have to do to the other. So you end up with a force of, number 14, let me double check, of 2,000 newtons. You're welcome. All right, moving on. Let's go to number 15. Or did I box my answer on the previous one? Oh, yes, I did. Look at me go. All right. So, number 15. Number 15, we have a mechanical advantage of an inclined plane. Okay, we have an inclined plane here, and it's going to be 5 meters long. So that is our length, or we could say, which equals our distance in, our DI. And it's 1 meter above the ground. So that can be our H or our DO, either way you want to look at it. Now, theoretical mechanical advantage is also the same as ideal mechanical advantage because that's what we would like it to be, or that's what it kind of should be if we don't take anything else into account. So, if I'm going to find the IMA, you can either use the DI over DO formula, or you can use the length divided by height. The length would be 5 meters divided by the 1 meter, so your IMA would be 5. There are no units because the meters cancels out. All right, so that answers that first part. Then it says, so that was my A answer. It then says, what's the actual mechanical advantage if 100 newtons of effort, so that's my force in, because I'm having to put 100 newtons in it, is needed to push a block that weighs, so that's your force out, of 400 newtons up the plane. So AMA's formula is what we're trying to use, which is FO over FI. So we're just going to say 400 newtons divided by 100 newtons, which is 4, because the newtons cancels out. So that's our answer for B. And then they want to know the efficiency for C. Well, efficiency is work out over work in, or AMA over IMA times 100. So we would have 4 divided by 5 multiplied by 100, which gives you an answer of 80%. Okay, remember there are 2 different formulas for efficiency, and that would be part C. Efficiency is either work output over work input, or actual mechanical advantage over ideal mechanical advantage. Moving on. Number 16. We having fun yet? Hopefully. All right. What is the efficiency of the body when a cyclist expends 1,000 watts of power to, can't even read that copy, mechanical energy, to do mechanical energy to the bicycle at a rate of 100 watts? All right. Remember, this is the same as anything else. If the out on efficiency goes first and the in goes underneath. Okay. So, and I think I just said that backwards. No, I didn't. Okay. How much power did we get out of the machine? We got 100 watts out of the machine. And we put in 1,000 watts. They want us to find efficiency. Well, another way to think about efficiency would be just instead of work out to put power out over power in, because it's always out over in, times 100. So we could say 100 divided by 1,000 watts, and they cancel out, times 100 equals, and you should get an efficiency of 10%. Remember, efficiency is always out over in, so that should be easy depending on whether it's work, power, whatever, it'll all be the same. 17. In the pulley system shown, ideally what force is necessary to raise the 10-kilogram weight with a constant speed? Well, the thing to realize is we first have to find the mechanical advantage, and that would mean that your IMA would equal. So let's count strands, because that's how we count, or that's how we figure out mechanical advantage. So we count all of them except the one we're pulling down on. So there's very visibly on that drawing 3. So that's going to be the mechanical advantage. And so if I want to find out force, then if that's my IMA, I'm also going to say that's my AMA. Well, the formula for AMA is force out over force in. Well, if I'm lifting a load of 10 kilogram mass, then that force is 10 kilograms times gravity, which is 10 meters per second squared. So 10 times 10 is 100 newtons. So I would say that 3 equals my 100 newtons over my input force, which is what I want to find out, because I want to find out what force is necessary. Remember, if it's at a constant speed, we have balanced forces, okay? But we have something that's going to help us out, so those aren't going to be exactly the same. So when we solve, we'll say 100 divided by 3 equals Fi. It's your algebra manipulation. So you should end up with 33.33 newtons for the first answer. So that's A. Now on B, it says if the object rises 4 centimeters, how far does the puller's hand have to move? Well, if that's how far the object's going to rise, that's my distance out. So that's going to be 0.04 meters when I convert. They want me to find the distance in because that's what my hand is going to do. Well, I need to remember that work out equals work in. So Fi di equals Fo do. So that's our FD photo. And we have our input force of 33.33 newtons times my di, which is what I want to find, equals my 100 newton force out times 0.04 meters. And now it's an algebra problem because 100 times 0.04 divided by 33.33 should give you an answer of 0.12 meters. And that's your answer for B. All right. Now we also have an efficiency here. Now, because we're going to have to talk about if instead of it being 100% efficient, it's only 40% efficient, what force is necessary to raise the 10 kilogram block at a constant velocity? Well, here's where we're going to have to do something a little different. All right. So I'm going to forward this to the next screen, but we'll still talk about this information. We know that the efficiency is now going to be 40%. Now, one of the efficiency formulas we have is AMA over IMA. Well, I'm not going to be able to say that IMA and AMA are equal to each other anymore because at the very beginning it said ideally they were. Now they're not. So I'm going to say 40%, which is 0.4, equals, I want to find my AMA over my IMA, which is 3, because that's how many supporting strands I have. When I multiply those two together, I find out that my AMA is going to be 1.2. Well, if I use the AMA formula, it's force out over force in. So if I now know that my AMA is 1.2, I know that my force out, I'm still moving the same weight, so it's 100 newtons. Now I want to find the force in if I change the efficiency of the machine. So it's 100 newtons divided by 1.2 would give me an answer of 83.33 newtons. All right, so let's continue on to number 18. 18, we're talking about a roller coaster that has a mass of 500 kilograms, and it's pulled to the top of a hill which has a height of 45 meters and arrives at the top with a velocity of 0 meters per second, so it's at rest. How much work is done by the chain that pulls the car to the top? So remember, this work we're going to say is equal to the change in potential energy. Roughly, the change in potential energy is going to be from the bottom at 0 up to the top, which is 45 meters. Okay, so we're just going to do mgh, and we're going to find the potential energy because that change in potential energy is going to equal our work. So we're going to say our mass of 500 kilograms times our gravity, which is 10 meters per second squared, times our height, which is 45 meters, because it's 45 meters minus 0 meters. Okay, when you multiply all three of these together, you should get an answer of 225,000 joules. And that should be your first answer on that problem for A. Then on B, it says, how fast will the car be going when it gets back to ground level? Well, all that potential energy that it now has is going to be converted into kinetic energy because it doesn't have any kinetic energy at the top because it's 0, and it doesn't have any potential energy at the bottom because its height is 0. So we have our 225,000 joules equals our mv squared over 2. Well, remember, our mass is 500 kilograms, so all we're finding is the V. So we're going to multiply by 2 on both sides, and then we're going to divide by 500 kilograms. All right. And now we're going to take the square root. Okay, so once we take 2 times 225,000 divided by 500 equals square root it. When you do that, you should get an answer of 30 meters per second. And that's your answer for B. Now on C, we want to know how fast the car will go at a point that's 29 meters above the ground. So remember that we're going to have kinetic and potential energy. So all the potential energy that we started with will have to equal kinetic plus potential energy. All right. Well, so we're going to go ahead and say that our 225,000 joules equals mv squared over 2. And we're going to substitute in for our m over here, our 500 kilograms, v squared, plus we have our 500 kilograms times gravity, which is 10 meters per second squared, times our height, which is now, according to the problem, 29 meters. So this part has a height of 29 meters. Now when you do the algebra, you're going to go ahead and do your 225,000 minus whatever 500 times 10 times 29 is. And then you're going to multiply by 2 and divide by 500 and take the square root. And I'm not going to show you all that because that's really just algebra. All right. So you should end up with an answer of 17.89 meters per second. If you need me to show you the algebra, come into class and I'll show you individually. All right. Moving on. Last one, number 19. All right. Number 19, we have the same roller coaster, so it's still a mass of 500 kilograms. And it's going to be pulled to the top of the 45-meter hill, just like it was a minute ago. And this time it arrives with a speed, though, so it has a velocity of 4 meters per second when it gets there. How fast will the car go when it hits the point of 29 meters, so that's my second height, above the ground? All right, here's the issue. We want to go ahead and at the top of the first hill we'll have potential energy, but this time we're going to have adding kinetic energy because it's got a speed when it gets there. That's going to have to equal all the kinetic energy plus the potential energy of the second hill. Okay, so we want to find the velocity at the second hill. So these are all my 1s and these are all my 2s. and that's what I'm finding. So I have mgh plus mv squared over 2 equals mv squared over 2 plus mgh. Now here's the issue. We have m's all the way across and we have 4 of them. So we can just cancel them out if we would like and not deal with the masses at all. We now have 10 meters per second squared times our first height of 45 meters, plus we have a 4 meters per second squared divided by 2 equals v squared divided by 2 plus 10 meters per second squared times our new height of 29 meters. We're now going to do algebra. Do not forget to do your squareds or add and subtract before you divide and multiply if on this one side. Simplify one side and then start isolating your variable. Okay, so you should end up with, on this side, you have 229,000 equals our our V, oh, actually, no, because I took out my other numbers. So that's not going to be right. I'm not going to do the math on here. So you should end up with a V of, let me get my thingy, a V of 18.33 meters per second when you end up doing your calculation. The reason for the second part, it says, why is your answer not your previous answer that we got an 18 just plus 4? And the reason for that is because kinetic energy is 1/2 mv squared. So because of the squared, that doesn't, you just can't add 4 and get the right answer. You have to do the square root and redo the calculation. All right. So because of the lovely little part right here, the V of number 18 is not equal to the V of number of 18C. It's not equal to the V of number 19. I hope this helps. Again, look over your notes because that's where your multiple choice and fill in the blank will come from. Check you later.